So in this one, I'm going to try and show why for small changes, log of 1 plus some number approximately equals the number. The log approximation. This is all kind of just off the top of my head. So don't interpret this as some kind of serious mathematical proof. This is mostly just for me to refer back to be honest. So, yeah, right, let's go. So, I've got a function here which is log of x, and for any x, right, I've just chosen this arbitrary x here, but you know, for any x, you can add some kind of some small change in x, right, delta x, and you get a new x which we're going to call x1, right? And same for the function, the log of x, right? The difference between log of x and log of x1 is just the change in log of x, delta log of x, right? So I'm just going to write these definitions here. So delta x equals the difference between x1 and x, right? x1 minus x, and here delta log of x, the change in log of x, equals log of x1 minus log of x. Okay, these definitions are important, so keep them in mind. I'm also going to quickly just rewrite this one here. Yeah, I'm just going to get x1 on its own. x1 equals x plus delta x. Okay, right, and there's one more definition that's important. That is delta x on x. What is that? That's a proportional change, right? The change in x on x, that gives you a proportional change. So we're going to call that g, like for growth rate. But whatever, could be any variable name, we're going to call it g. A proportional change in x is g. So let's take this equation here. Delta log x equals log of x1 minus log x. And I'm going to substitute this x1, just write this out again, equals log. I'm going to plug in our definition for x1 up here, x plus delta x minus log x. And using the properties of logarithms, right, we know that this is the same as log of x plus delta x on x, which we can write as log of 1 plus delta x on x. What's delta x on x? A proportional change. We defined that earlier. That's g. So we can write, we'll take our original delta log x equals log 1 plus g. Okay. We're trying to show the log approximation. So we're trying to show that log of 1 plus g equals, or you know, approximately equals g, right? So and for infinitesimally small changes equals g. So in order to show that, right, we need to show that this here, delta log x equals g, which is delta x on x. So how can we show that? Well, this is where the assumption of infinitesimally small changes is crucial, because here we're going to use calculus. So if y is our function of x here, which is log x, dy dx is, or we can write it like that. What's that? We know this from calculus. It's 1 over x. Yeah, our first derivative of the natural log, 1 over x. We know that. So I'm just going to multiply across here by delta x. So we get delta log x equals delta x over x. Now we're familiar, by now we're seeing this. What is that? That is g. So we've got delta log x equals g for infinitesimally small changes. So here we can just write equals g. And this bit here, log 1 plus g equals g, that is our log approximation.